In Theorem 4.1, we are going to discuss a criterion when two powers of a group element are equal to each other, and how we can be sure that we have everything in the cyclic group generated by A enumerated. So let's read the theorem together. Let G be a group with A an element in the group. If A has infinite order, then all distinct powers of A are distinct group elements. If A has finite order, let's say the order of A is n, then what is in the cyclic group generated by A? What do we actually have to write down? Well, we have the identity, we have A, we have A squared, and so on. Where can we stop? Do I have to write them all down, or can we stop at some point? And the fact is, we can stop at A to the n minus 1, because A to the n would be the identity again. So we can stop right there. And then we also have that two powers of A are equal to each other if and only if. What has to be true? What do you think? It has to be true that n divides I minus j. That is a criterion for two powers of A to be equal. And we're going to prove some of this. We are only going to discuss the finite case. So we are only going to write a proof of the finite order case. And so what do we need to do? There are actually three things that we have to deal with. We have to show that all of these elements that we enumerated, they are all distinct. We have to show, oh, distinct, I wrote that wrong, distinct. We also have to show that this list is complete, that we captured all powers by writing down only n. And then we have to show this if and only if. So for A to the I equals A to the j, if and only if n divides I minus j. So there are three things that we want to discuss in this proof. Okay, let's do it one by one. What is our assumption? Well, our big assumption is we have a group, we have an element in the group, and the order of that element is n. So let's assume the order of A is equal to n. Okay, first thing we want to discuss is how do we know that all those elements have to be distinct? Well, let's think about that. So the elements E, A squared, A to the n minus 1 are all distinct. For what would happen if they were not? So for if we had that A to the I is equal to A to the j, something is going to go wrong. And so let's assume that A to the I is equal to A to the j for an I less than a j. This is arbitrary. I could have gone the other way around, but let's just go with one of them has to be less than the other. So let's just assume I is less than j. So what would happen if A to the I is equal to A to the j for some I less than j? Well, we can take A to the j inverse on both sides, multiply by A to the j inverse, so A to the minus j on both sides, and that is going to give us the following statement. So that would give us an A to the j minus I, is equal to E. And I gotta fix that. I actually took minus I. Let me fix that. I didn't want minus j, I wanted minus I. And the reason that I wanted minus I is because I is less than j. And I just want to deal with powers bigger than 1 if possible. So anyway, I have a to the j minus I is equal to the identity. But what does that mean? But that implies that the order of A is actually less than n because j minus I is less than n. So it would imply that the order of A is less or equal to j minus I, which is less than n. And that's a contradiction. Because we assumed that the order of A is n. And so now we have concluded that the order of A would have to be strictly less than n if A to the I was equal to A to the j for some j less than I less than j less than n. So that covers the first part. So the first part so we can conclude all of those elements have to be distinct. Okay? Then do we have them all? So this was like the first little piece. The second little piece is, does my cyclic group generated by A capture everything? So does it give me all my powers? If I only write down n elements, do I get every single power? Okay, well, let's see. Let's pick one. Let's take an arbitrary element in the cyclic group. So A to the k is some element in A for some k. Now comes the part why we looked at the division algorithm a few modules ago, or at the beginning of the course. So if A to the k is an element of my cyclic group, then by the division algorithm, there exists a Q and an R in Z such that we can write this k as q times n plus r. So we're applying the division algorithm, dividing k by n. And so that gives us our quotient q and our remainder r. And the remainder has to be between 0 and definitely less than n. Okay, but so now let's use that. So thus, how come we can write a to the k as a to the qn plus r? And then we can write that as a to the n to the q times a to the r. But a to the n is the identity. This right here is our identity element, and the identity to any power is still the identity. And so we succeeded in writing this as just a to the r, where r is between 0 inclusive and not inclusive, exclusive. And so this is definitely one of our elements. It's e, or it's a, or it's a squared, or it's a to the n minus 1, because we are just dealing with a power that's a remainder after division by n. So we showed the second part of our statement that we needed to show. So that's great. So we have that they're all distinct, and we have that we capture everything. So the last thing we need to show is the if and only if statement. Okay, let's deal with the if and only if statement. So does a to the I equals a to the j imply, and the other way around, that n divides I minus j? So let's deal with that statement. And instead of doing two directions here, we are just going to do a bunch of if and only if statements. All right, so we're going to start with the right-hand side. So assume n divides I minus j. Then what does that mean? That is equivalent to saying that I minus j is a multiple of n. We talked about that in an earlier chapter. So we can write I minus j as n times k for some k in z. So that was one of our, just the definition of division. So, but if that is true, then if we take a and raise it to the left-hand side, that is a raised to the right-hand side. So we have a to the I minus j, and that is equal to a to the nk. And that we can rewrite as a to the n raised to the k for that same k. I don't need to write that down again. Never mind. Okay? And then what happens? Well, a to the n is equal to e still. We already used that before. This is our identity. And so we have that a to the I minus j is equal to the identity. But now we can do that same thing that we did before. So this if and only if you multiply both sides by a to the j, then you have an a to the I on the left-hand side and you have a to the j on the right-hand side. And we succeeded in just writing down equivalent statements and showing that a to the j is equal to a to the I, or a to the I is equal to a to the j if and only if n divides I minus j. And that completes our proof.